morning everybody. I am Manasa. I am from CSC department. I am going to take the topic called deadlocks. Here, what is actually a deadlock? Deadlock is a situation where one process requests a resource and the same resource is also requested by another process. That situation is called as a deadlock. And here we have few examples of computer resources, the basic needs. Here we'll take printers, tape drivers, tables. Process which needs access to resources in a reasonable order. Whatever processes we are using, the resources which we are using in that process, that should be in a reasonable order. Suppose a process holds a resource A and requests for the resource B at the same time. Another process holds B and requests the resource A. Then both are blocked. Okay, this situation is called as a deadlock situation, wherein I'll draw an example. Deadlocks occur when processes are granted exclusive access to the devices. Here, when deadlocks occur, we have an exclusive access that is given to the resources. Generally, these devices are called they are referred to as resources. Preemptible resources can be taken away from a process with no ill effects. Here, when a process is using a resource, then if we remove that resource when the process is using, then that is called as preemptible resources. Non-preemptible resources, when the process is going on, when the process is using a resource, if the process is taken away, then that process will be failed. The next one comes as sequence of events requested to use a resource. How are we going to use the resource? Request the resource. First, we are going to request the resource, then use that resource, then release that resource. The next thing is must wait if the request is denied. Requesting processes may be blocked or may fail with some error code. If any process is requesting a resource, then it can be denied with two reasons. That is, one is either if it is blocked or if you have any error in that resource. The next one is introduction to the deadlocks. It is a situation where a set of processes is deadlocked if each process in the set is waiting for an event that only other process in the set can cause. What all they cause? Usually the event is release of a currently held resource. None of the process can run, release or be awakened. Here what happened is when one process is using a resource, when another process wants the same resource, when the first process releases the resource, then only the second process can use that resource. None of the processes can be, if it doesn't release the resource, then none of the processes can be run, or you cannot release the resource, or it cannot be awakened. In the next screen, here we are going to talk about a multi-programming environment. Several processes may compete for a finite number of resources. A process requests resources if the resources are not available at that time. The process enters a waiting state. Normally, if a process doesn't get the resource, then it enters into the waiting state. Sometimes waiting processes is never again able to change state because the resources it has requested are already held by other waiting processes. Sometimes some changes are there when the process is waiting in the queue, it doesn't get a chance to use that resource because for that resource already one more process will be waiting there. This situation is called a deadlock. Then here we have few necessary conditions to check whether the condition, the process or the resource is in deadlock or not. What happens here? Mutual exclusion. Here each resource assigned to the process is available. One resource will be available for one process. Whichever a process requests the resource, it will be available. That is called as mutual exclusion. Hold and wait condition. The second condition is hold and wait condition, wherein one process will be holding one resource and it will be waiting for the other process to enter. But that resource, it will be waiting for the other process. But that resource is already held by the other process. So it will be a deadlock situation. Here, no preemption condition. Previously granted resources cannot be forcibly taken away. Here, what happens is the condition, the conditions where the resources are used, that when the process is using a resource, that cannot be forcibly taken because that is non-preemption. Circular wait condition. Must be circular chain of two or more processes. Each is waiting for resource held by the next member of the chain. Here what happens is one process is holding the resource and the same resource is already held by the second process. If the first process releases the resource, then only the second process will be able to use the resource. If that second, this is called a circular condition. Here, this is resource. A resource is, I've mentioned it using a square box, and here it is a directed graph where a process is, I've mentioned it with a circle. Here, our resource R is requested by process A, and here process B is requesting or waiting for the resource S. Here it comes to the condition that circular wait condition. Here all the resources are waiting for the processes and the processes are waiting for the resources. Strategies for dealing with deadlocks. Just ignore the problem together. If it is a situation where the circular wait isn't possible or any issue with the deadlock, then you can just ignore the problem, and you have two concepts there, detection and also recovery. And the third one is dynamic avoidance also is present. Careful resource reallocation, prevention, negating one of the four necessary conditions. Okay, one condition can be removed from the deadlock necessary conditions. Here is an example wherein resource A is requested by process A. Here resource A is requested by process A and resource S is requested by process B. Here three resources are requested by three processes. Here the fourth condition, next condition will be resource A is already using process A is already using resource R and it wants resource S also. Here process A is using R, it wants S. Process B is using S, it wants T, and here process C wants resource R. This is a deadlock situation wherein here it satisfies the circular wait also. If that is the condition, what happens? Here resource R is requested by A, and here we can avoiding the deadlock. How are we going to avoid? Resource R is requested by A, and then we are going to break that chain and we are going to use resource T is requested by C. After C is done, S will be requested by A, and once it is done, this resource will be available. When this resource is available, process C can use resource R. In the same way, it can release R and it is available to C. This is using this, and here this is releasing that and using the same resource. Here this is one more thing. Note that the resource ownerships and request cycle can be found within the graph, denoting deadlock. Here you can find a cycle with a directed graph. That means it denotes that it has a deadlock. Here in B condition also we have a deadlock situation. This is a matrix. Denotion of deadlock detection is used by a matrix. Current allocation matrix and request matrix. Here recovery. How are we going to recover the deadlock? Recovery through preemption. Take a resource from some other processes, depends on nature of the resource. In the same way, in the previous example which I have told you, in the same way, when one process is requesting a resource, then take the resource from other process, so that the first process will release the resource. Depends on the nature of the resource. When the second condition is depends on the nature of the resource. That means the resource is already, if that resource is already using, then it cannot give its own resource. So it has to wait. Recovery through rollback. Checkpoint. You will have a checkpoint in between. Whenever you want to check the resource periodically, is it done or not, or it is released or not, then you will be coming to that checkpoint, and then you will be checking for the next resource. Use the saved state, restart the process if it found deadlock. If you found a deadlock or circular wait, then you can restart the process. Here, recovery through killing processes. Crudest but simplest way to break a deadlock. Here, if we want to avoid a deadlock or if we want recovery, then you're going to kill one process, or kill one of the process, the other process gets its resource. Then choose process that can be rerun from the beginning. That process which we are selecting to kill, that process should be like a resource which can be rerun from the beginning. These are the graphs. Here you can say, in the last I am going to explain about the banker's algorithm, wherein we can save the state as tell the state is safe or not. The conditions here are safe state, unsafe state. If the process is in safe state, then it's fine. But if it is an unsafe state, we are going to use the banker's algorithm and make it safe state. Some devices such as printer can be spooled. Only the printer uses the printer resource. So thus deadlock for printer eliminated. Once if we are using a printer, for example, if we are using a printer and if we give some sheets to print, when that is going on, we cannot break it in between. If we break it also, no use. Not at all the devices can be spooled. Principle is avoid assigning resources when not absolutely necessary. If we avoid those which are not completely necessary, then we will have some resources left out. As few processes as possible actually claim the resource. The other processes which are in need of resources, they can claim the resource. Attacking the hold and wait condition. Require processes to request resources before starting a process, never has to wait for what it needs. If you hold some process, if other processes require those, it needs some time to wait. But if you are using that, and if once your process is done, then you can give that resource to the other ones also. Problems. May not know required resources at start of run. Also ties up the resources other process could be using. Here you have variations. Process must give up all the resources, then request all immediately which are needed. Here the same condition which I have explained you, attacking the no preemption condition. If once the process is going on in the printer, suddenly if we want to break the job halfway through its job, Now forcibly take away the printer. Is it possible or not? Then here comes the circular weight. Normally ordered resources, a resource graph. You're going to whatever, you'll have a directed graph wherein all the processes and resources are given. That processes and resources, if it forms a circular weight, then you'll have that condition. Mutual exclusion, approaches, spool everything. Hold and wait, request all resources initially. No preemption, take resources away. Order resources numerically. Then in the phase 1, what happens here is process tries to lock all records it needs, one at a time. Whatever records it needs, resources it needs, process blocks one at a time, and it uses the another resources. If needed record found locked, then it will be starting from the first phase. If the phase 1 succeeds, it starts second phase, performing updates and releasing the locks. Once the process is done, it releases the locks. Note the similarity to the requesting all resources at once. Here we have an algorithm wherein programmers can be stopped. Possible for two processes to deadlock. Each is waiting for the other to do some of the other task. If two processes are waiting for two resources, then here it may form a deadlock. It can happen with immense semaphores. Each process is required to do down the two semaphores, mutex and another. If done in wrong order, deadlock results. Here, if it is done in a wrong order, then deadlock occurs. Here you have another condition is also there, wherein starvation. Starvation is a situation where processes will be waiting for the resources, but those resources will not be available as those resources are already used by another processes.